Well, that kind of looks like it. Yeah. Good. Hi, everybody. Welcome to the first physics colloquium of the fall season. We decided this year to start off with something a little different because there's a lot of very interesting experimental science that's physics-based out there, particularly in the...
Bob, use the microphone, please.
Can you hear this? No. That sounds okay. That's good. So yes, we decided to do something different this year because there's an immense amount of excellent physical science done right next to us here on campus. I thought we should find out a little bit about it. And it pertains to things that we really care about, which is the time scale of beat time. But in this case, it isn't in outer space, it's right here on Earth. I snooped around a little among my geophysics colleagues, and I found by unanimous consent, the person who should be talking to us is Professor Mark Harrison from UCLA, who has kindly offered to talk to us today. Now, I asked him for bio stuff, so there's some bio stuff. I'll leave. He's got a very distinguished career, moving all over around the place, running the Geophysics Center at Australian National University. He's a member of the National Academy, well known here at Stanford. And his interests, I will say, are pretty broad. He is a geochronologist by focus, but his interests, he says, are in the near and the far. So he's interested in the early, or very early Earth, which is about as far as it gets, as deep as it gets with the Earth. And also some issues of more recent times. He mentioned particularly the way in which India collided with Asia to make the Himalayas. He's a very peripatetic geologist and just a terrific intellectual. And I think we're going to have a nice show today. Anyway, without further ado, I introduce Professor Harrison.
Thanks. Yeah. Now this is just for the record. I need this one too, do I?
Fine.
Yeah. Well, thank you very much, Bob. Yeah, we're good? Oh, here we go. Oh, I see what I did.
Wait, it's not on. Wait, let me turn it on. Theorists are good for something.
Yeah. Yes. Yeah, clearly an intellectual. Well, there's all societies have origin myths. As long as our species has been roaming the planet, we've been speculating how and when it formed. Now, for the last 3,000 years or so, we have evidence, we've been quantifying it. According to the Hindu Vedas, we're about one day, one kalpa into the present life cycle of Brahma, and that makes the planet about 4.32 billion years old. So you got pretty good estimate. Interestingly, the ancient Greeks didn't think much of finite time. They thought that the planet was eternal, so they didn't really get into this debate. But by the early first millennium, biblical scholars were using the chronology in Genesis. Adam begat Seth when he was 130, and Seth begat Enos, and so on, and adding it up to determine when the planet formed. And this culminated in 1654 with the publication of Archbishop Usher's book, in which he determined that the planet started at twilight, October 22nd, 4004 BC. Now, come the Enlightenment, we start to get estimates based on physical mechanisms. Comte de Buffon had 10 iron balls of different diameters fabricated, put them in his forge, watched how they surface cooled from white incandescent to glowing red to cold, and then extrapolated to the diameter of the Earth and said the planet was 75,000 years old. Helmholtz could only conceive that the sun's luminosity was due to gravitational infall, so he calculated that the solar mass could produce that output for about 20 million years. And the most famous one, William Thomson, later Lord Kelvin, calculates an age of about 100 billion years from the decay of an initially molten Earth to the present apparent geothermal gradient. Now, this is not only the most famous of these Victorian estimates, it also illustrates the positive aspects of engaging physicists in geology, but also some of the pathological aspects as well. So let's have a close look. So what he assumed was that the planet formed what he thought was the melting temperature of iron, which he wildly overestimated as close to 4,000 degrees. So here's the Earth's surface. He used Fourier's solution for semi-infinite solid, conduction down here, radiation at the surface. And after between 10 and 200 million years, you can see that the near surface geothermal gradient decays to its present observed value, which he got about right at 35 degrees per kilometer in about 100 million years. So here's the calculation here. The age of the Earth is the initial temperature, the near surface geothermal gradient, squared divided by pi, and the thermal diffusivity, which he also got approximately correct. And after a few years, he recognized he'd wildly overestimated the melting temperature of iron, so he redid the calculation for 1200 degree initial temperature, and you can see that you'll drop through that 35 degree per kilometer gradient in 10 or 20 million years, so further reduce the estimate. And classically, if you look at geology textbooks even today, or intro textbooks, this in fact is what geologists were up against. They thought this was way too short a period to have in fact had the species evolve according to the then known rock record, and that this dominated the debate until 1897 when Becquerel discussed radioactivity. And this is because radioactivity generates internal energy, and this could keep the Earth hot for a much longer period of time than Kelvin thought. But the Earth's presently losing about 45 terawatts of heat. But our best estimates of the heat-generating isotopes of potassium, uranium, and thorium is that they're generating about 20 terawatts. So if you were to go back in time and say to Kelvin, here's 20 terawatts of heat, and you can distribute it how you like, his calculation, instead of being the dashed line, would be the solid line. So you're still going to drop below 35 degrees per kilometer near surface gradient in a couple of tens of million years, because the problem is not one of the loss of heat from a thin thermal boundary layer, the surface of the Earth. In fact, now that we understand the global plate tectonic system, we know Earth structure. We've got essentially stainless steel inner and outer core, a hot rocky mantle that appears to be convecting in a fluid fashion, and this rigid thermal boundary layer up here in which heat really is only flowing by diffusion. And we call that the lithosphere, and it's about 100 kilometers thick. Well, interestingly, a contemporary of Kelvin, John Perry, used a Heaviside operator method to construct the conductive thermal model that had two layers. One, astonishingly, about 100 kilometers thick, below which a region in which the conductivity was, the diffusivity was 10 times higher to simulate fluid convection. And he got an age of the Earth of 5.5 billion years. Now, interesting, Kelvin responded to this in the pages of Nature and said, yeah, 5 billion years, that's within uncertainty of my estimate. So, in fact, it wasn't radioactivity heating the Earth that transcended Kelvin's calculation. It was the fact that you could actually date rocks. And just shortly after Becquerel's discovery, Rutherford, in fact, in 1905, was reporting uranium-helium ages. I'll explain these methods in a sec. As old as 500 million years. Boltwood, a couple years later, 2.2. So you can see by the roaring 20s, we know a minimum age of the planet of 3 billion years. And again, in the introductory textbooks, even today, the end of this story is in the mid-50s when Clair Patterson determines the age of the Earth to be 4.5 billion years. Now, let's actually look at these systems in greater detail. Two long-lived isotopes of uranium, 238, 235, decay to isotopes of lead, 206, 207 respectively, with half-lives, one about the age of the Earth and the other about 1/6. Fortunately, there's an isotope of lead, 204, that is neither radioactive or itself the product of radioactive decay. So we've got the same amount of 204 we started with when the solar nebula collapsed 4.5 billion years ago. The uranium isotopes don't decay directly to the lead, but through a series of intermediate daughters. They alpha decay along this trajectory, beta decay, and then alpha decay down here. So in fact, what Rutherford was doing was measuring the amount of helium, the alpha particles, that were accumulating in minerals. And because helium is rare gas and a small molecule, small atom, it can escape from minerals. So it was thought to be a lower bound. For 235, the longest lived intermediate daughter is only 32,000 years. So it reaches what's called secular equilibrium within 250,000 years or so. 234, uranium, has a half-life of close to 250,000 years. So you have to wait in this decay system 1 million years before one decay of uranium-238 corresponds to the appearance of one atom of lead-206. So keep that in mind. But in secular equilibrium, Rutherford said, look, the age of a mineral is simply the daughter-to-parent relationship. The amount of accumulated daughter lead-206 over 238 divided by the decay constant, the fraction of 238 atoms decaying per unit time. The really cool thing is that we don't expect uranium isotopes, 235 and 238, they're so massive, to fractionate from one another under really any natural geological process. So we can assume that they're in a constant relationship, that there's 137.88 times more uranium-238 than there is 235 today. So we can calculate an age, that's the little t here, by dividing this equation by this one, rearranging, and the radiogenic lead-207-206 ratio is a function of age. We need to iteratively solve this equation, but it's cool. It means we don't have to measure the parent abundance. Simply the ratio of these two daughters gives us the age. So the early estimates of the age of the solar system, we're using this so-called lead-lead dating. So here we have the 206 divided by that normalizing isotope. Why do we need it? Because a relatively small fraction of lead in any geological sample is produced by in situ radiogenic process. Most of it, in fact, is going to be common lead. So in this particularly interesting system, 6,4 here, 7,4 here, you can see the slope of a line on this plot corresponds to the 207-206 ratio, which is implicitly age. So here's an age of 4.5 billion years. And what scientists in the 1950s found was when you took primitive meteorites, okay, objects that fly in from outer space that represent the earliest materials that formed, condensed from the solar nebula, they plot on that line. Okay? Now, how you get on this line is interesting. There has to be a starting point before the day the solar system began, and there was no radiogenic ingrowth of lead isotopes because there had been no time for uranium to decay. There has to be a single point, and we get this, in fact, from Meteor Crater. The iron meteorite that flew in, Canyon Diablo, has a mineral in it, an iron sulfide called troilite, that has no uranium but lots of lead. So this is the initial lead isotope composition of the solar system. And if you have no uranium, you'll never move away from that point. But if you have a uranium-lead ratio, and this is mu, is the ratio of uranium to that primordial isotope of lead. If you have a value of 10, you'll evolve along a trajectory like that, 3 billion, 2 billion, 1. This is the present day. What they found was that meteorites have an age of about 4.5 billion years. Now today, we have exquisite instrumentation and chemistry, and we can measure lead isotopes, other isotope systems, to a few parts per million. And I liken this that if it's Saturday, the Stanford Cardinal are playing Cal, and the stadium is packed, and one person gets up out of that stadium, goes to use the facilities. The mass of that stadium has changed 50 times more than our ability to measure an isotope ratio today. It's astonishing. So here's a primitive meteorite, Efremovka. It's got some, so this basically is the stuff that condensed out of the solar nebula back when. It has a few things in it. This stuff here is called a CAI. These are the first solids to condense from the solar nebula. When did it happen? Well, you can see they sit on this. This is a modified version. It's lead 206, 207, 206 versus 204, 206. It's a different formulation of that same principle. And the ages are exquisite, 4,567.17 million years with better than a million-year accuracy, precision. Now, interestingly, they're called chondrites because they have these dark round features called chondrules. And you can date chondrules, and they're 3 million years younger in virtually all these primitive meteorites. So in the 50s, scientists, the techniques weren't as good as ours, but they got the idea that the meteorites are about 4.5, a little older than 4.5 billion years old. Clair Patterson, who's given credit for determining the age of the Earth, he said, look, here's Canyon Diablo Troilite. That's the object that made Meteor Crater. Here's a couple of undifferentiated meteorites up here. And look, if I take 3 samples from the Earth, clay at the bottom of the abyssal plains in the ocean, manganese nodules forming in the oceans, and basalts, lavas that have recently erupted from the Earth's mantle, he said, these should be good representations of the average composition of the Earth. It's the sediments particularly, because they're going to be averaging material that's eroding from all over the planet. And he said they plot on the same line as the meteorites, so the Earth is 4.5 billion years old. QED. Well, there's a problem with this, and that is that the assumption here is that the source of these sediments and of this lava has been essentially differentiated instantaneously 4.5 billion years ago, and then remained a closed system ever since. And as we understand now, the global plate tectonic engine, this is not the case, that our planet is in fact essentially continuously dynamically recycling material, mixing material. There is simply no place on the surface of the planet where you could find a rock that is a representation of the closed whole Earth system. That just is not conceptually possible. So the assumption that Patterson made, in retrospect, is not valid. And indeed, when we now, with our exquisite techniques, look at these, marine sediments don't plot on the geochron. And basalts, very few of them actually plot close to this line. And that makes sense because our Earth is differentiated. Okay? It has in fact undergone chemical fractionation that's produced that metallic core, a very silica-rich crust. And I almost knew the dance step to that. Right? That's right. I got to get my underwear to do that, right? The Tom Cruise movie. So, in fact, this did, and again, in the textbooks today, the end of the age of the Earth debates ended, but in fact, only because we all agreed to look past these fundamentally problematic assumptions. Okay, how do we take this highly fractionated, evolved, differentiated body, for which no rock on the surface of the Earth could possibly represent the average property of the whole Earth system? I mean, I could take the whole Earth, put it in a giant mortar and pestle, and crush it up, scoop that up. That material would plot on the geochron. It would plot on the meteorite line, okay, because we've been a closed system. But no part of the mantle or the core or the crust of the lithosphere, in fact, hasn't experienced open system behavior to, in fact, remove it from representing the bulk Earth. Okay, well, let's, in fact, look at this dating system here. This is a weird one. Hafnium 182, probably made in a supernova shortly before solar system formation. We know it's around because we can look at these chondrites, these primitive meteorites, and we see evidence of its decay product, tungsten 182. Now, this is a great system because tungsten is what we call a siderophile element. It loves hanging with metals. So you make an Earth that separates a metallic core from a rocky mantle, and you know where the tungsten's going. It's going straight into the core. Hafnium is lithophile. It's rock-loving. So here's hafnium. Here's tungsten. These things are, there's radioactive live hafnium 182 in the early solar system. Let's look at chondrites, and then let's look at the Earth's mantle samples, for example, like that basalt I just showed you, and see what they have to say. So here's the formation. We're made up of all these building blocks of meteorites, iron meteorites, rocky material. Eventually, the Earth's hot, the dense metallic material is going to sink and start forming the core, and as it does, tungsten is going to be partitioned into the metallic part and hafnium into the silicic crystal. So the flow diagram looks like this. Chondrites have a hafnium-tungsten ratio of 1.3. We differentiate into a rocky mantle and a metal core. The lithophiles go into the mantle and the crust with a high hafnium ratio. The iron core doesn't like taking any hafnium, so it has a hafnium-tungsten ratio essentially of 0. So in fact, when we look at chondrites, okay, here's the initial solar system. We look at, say, Canyon Diablo. This is the value of tungsten 182 over 183. 183, again, is this primordial isotope that we can use to normalize. Okay? And because of the relatively short half-life, 9 million years, after about, 50, 60 million years, all the hafnium 182 is decayed, and today we can measure this value, as I say, with this exquisite precision. But where's the Earth's mantle? The Earth's mantle plots up here. So, a simple model says, look, we know that what the hafnium tungsten ratio in the mantle is. Let's extrapolate that back to the chondritic evolution line, and we get an age of about 30 million years. Okay, so we haven't dated the age of the Earth, but what we've done is said, we've got a pretty good model that says 30 million years on average after the first solids formed in the solar system, the Earth is big enough that it's segregated a core and that process has essentially been complete. Okay? So we've now got a lower bound. Now, uranium-lead is cool in a different way. If we can find a system, if we can find a mineral or a rock that in fact can behave as a closed system, it's got a lot going for it. Let's plot those two age equations I showed you early. Let's plot the ratio of 207 to 235, which is e to the lambda t, the decay constant times the age, minus 1, and here's 206, 238. This line here is simply parametric in time to these two equations. So a mineral that forms 4.5 billion years ago, okay, has a 207, 206 ratio, that slope there, that corresponds to 4.5 billion years. But here's the cool thing. Let's say yesterday we leached 99% of the lead out of that mineral. Okay, so we brought it all the way down here, and it plots not quite at the origin, it's still got 1% left. The 207-206 ratio in that mineral there, that's lost 99% of its daughter product, still tells us the mineral's 4.5 billion years old, because it's still on that same 207-206 trajectory. Well, we use this system in conjunction with a mineral called zircon. Okay, it's zirconium silicate. It's pretty simple. It's some cheap costume jewelry made out of it, but which is, you may have heard the term before. But geochemically, it's a miracle for us. Okay, why zircon? Well, of course, zircon is made up of zirconium, silicon, and oxygen. But like every other mineral under the sun, it's got a little bit of every other element in the periodic table in it. Some, it's got a lot. For example, zircons have typically got 2% hafnium in it. They've got a lot of uranium and thorium. The zircon structure loves uranium thorium, but it hates lead. So it excludes lead, concentrates uranium thorium. This is a great mineral for uranium lead dating. Likes the heavy rare earths, kind of likes the light rare earths. It likes plutonium. And there was a fair bit of plutonium. 4.5 billion years ago, we had the ratio of uranium to plutonium was about 100. Okay? So there was a lot. Plutonium-244, we're going to be able to use that for our purposes. It doesn't much like titanium, but it turns out that the concentration of titanium in a zircon tells you the temperature that zircon formed at. Okay. Anyway, and we can measure oxygen isotopes. That's going to turn out to be interesting. And I'll tell you a little later about lutetium hafnium dating. There's lutetium, oh, there's lutetium there, which decays to hafnium as well. To date these minerals, we use a device called an ion microprobe, essentially a very large mass spectrometer. It has a source of ions. We can focus this ion source down to just a couple of microns in diameter. We have a polished geological sample, a zircon, that we've put on a plastic mount and polish the surface. That primary ion beam sputters secondary ions from that sample, or atoms, some of which are ionized. We go into this large radius mass spectrometer, and we in fact can count uranium isotopes, lead isotopes, hafnium isotopes, and so on. And I also point out that we can use this device to, in fact, with an order of magnitude more accuracy, measure carbon isotope ratios. If there's time, I'll talk a bit about that too. Okay, here's a timeline showing major events in the evolution of Earth and life. And here we're up here. The bright colored part down here is the period of Earth history between about 4.5 and 4 billion years, for which today we have no known rock record. Nobody's found a rock older than 4 billion years on the planet. And for 50 years, 60 years, the assumption is that we haven't found a rock that old because they don't exist. That the first 500 million years of Earth history was characterized by a molten surface. There were no continents, no oceans. There was no life. And the only interesting thing was periodically objects would fly in from outer space and smack into this molten substrate. Now this is interesting. This is from the month after I was born. But here's some lines from a book published this millennium. And so not only is the sentiment the same, that for hundreds of millions of years, your surface was molten, but what's interesting is, apparently in this early Earth, you had to have these two little bumps appearing on your surface. Well, I mentioned earlier that all societies have origin myths. Some societies have multiple origins, okay? Like take ours. For 60 years, the scientific community has said that the first several hundred billion years of Earth history, from 4.5 billion years to about 4, the planet was desiccated, no continents, no life, and so on. But at the same period of time, if you look at polls that have been taken since the 1960s, about half of the American citizens believe that the planet is less than 10,000 years old and formed in the fashion of Genesis verses 1 through 9. Now what's fascinating is that despite the fact that these two views of Earth evolution differ in time scale by nearly a factor of 1 million, they share this in common. I see them as intellectual cousins, okay? Because there is absolutely, positively not a single scrap of empirical evidence that supports either or requires that either of those two views be true, okay? Neither the creationist view nor the view seemingly uncritically adopted by the scientific community for 50 or 60 years. So the warning here, the message is, if we're going to speculate, if we're going to think about the earliest phase of Earth history, let's restrict ourselves to tangible evidence. And what do we have? Can we know about the earliest Earth? Well, one is we can assume that physical laws are constant through time, so we can calculate that radioactivity would have been about 5 times higher 4.5 billion years ago than today. In mantle rocks, we have evidence of some short-lived radioactivities, like we've spoken about, like hafnium-182, that tell us that there was a dramatic global-scale differentiation event within the first 100 million years of Earth history. And we have these little guys. We actually have zircons, little minerals, that get to be almost as old as 4.4 billion years. We have no rocks older than 4 billion years, but in a 3 billion year old geological deposit, a quartzite in Western Australia, these rocks here, they contain detrital zircons that were deposited in this rock by sedimentary processes that are as old as virtually 4.4 billion years. So we can talk to these zircons and ask them questions about how they formed. And I'm not going to attempt to justify any of these points here other than to say that there's peer-reviewed literature that in fact supports the view that their oxygen isotopes say that there was very likely clays in the source rocks that melted to form those zircons. Well, a clay is a hydrous mineral. It has structural water in it. There is no water at or near the Earth's surface in the Hadean. How did you get this oxygen isotope distribution? The melting temperatures, remember from the titanium, they tell us that these granites formed at extraordinarily low temperature. That's as low as you can get and make a granite, and the only way you can do that is that the rock is essentially water saturated. That means it has to have 15 to 20 weight percent water in it, 70 to 80 mole percent water to get the melt that low. The minerals, here's a zircon, it's a cathodoluminescence image of a fragment of a zircon. It's like a tree ring. There's the core of the zircon. These are the growth rings in the magma from which it formed. Every zircon that ever grew takes little bites out of the melt around it, or the crystals that are in the melt. And in this case, 2 minerals, biotite and hornblende, formed. Down here, muscovite. These are hydrous minerals. They've got between 2 and 4% structural water in them. The source of these rocks had to have water. These minerals, muscovite and quartz and feldspar, today, if you look in the geological record, the simplest explanation for a rock that has this composition is that it's melted sediments that have been recycled at an active surface in the presence of water. We can not only do thermometry in these zircons, we can do barometry. We can look at the depth at which they formed, and using Fourier's law, we can calculate the near surface geotherm. Now, what's fascinating is this is within a couple 100 million years of the formation of our planet, and the heat flows range from about 30 to 80 milliwatts. What's striking is that value there is the present day average global heat loss of the Earth. So this is back when there's 5 times more radioactivity, when we've got all that primitive heat that's just been realized on this Earth forming through the violent collisions, and yet the near surface heat flow is a fraction, okay, of the present day value. Well, where on Earth today do you make molten igneous rocks carry a background that's characterized by a geothermal gradient that's 1/3 or 1/4? The geologists in the room know the answer to this. It's called a subduction zone. This is where plates meet, and one gets subducted, producing volcanoes like Mount St. Helens. I'm going to talk a lot about this, okay? This is the unradiogenic hafnium isotopes. I'm going to come back to this. I mentioned plutonium. There's actually, a lot of plutonium, but the interesting thing is when we look at the fission products, the xenon isotopes of plutonium and uranium fission, it indicates that they were variably separated. And the only geochemical way to effectively separate uranium and plutonium is through an aqueous process. Again, more evidence. The redox state of these zircons, I won't explain the diagram, but they range from being about as oxidized as the modern upper mantle to 4 orders of magnitude more reduced. And the geochemistry of these zircons, these are not from the moon, these are not from oceanic crust, they didn't pop out of the mantle in any way, these are continental zircons, okay? So the simplest explanation for everything that we see in these little ambassadors from the Hadean is actually that the planet was behaving much more like the present day than previously believed. At least, my explanation is not unique. I think it's the simplest way to explain everything that I've just shown you. But the one advantage I have in my model is that there's actually evidence for it, whereas the community for 60 years accepted this idea of this protracted molten surface without there being, in fact, any observational evidence. Okay, let's look at this lutetium hafnium method, lutetium-176. It's got a very long half-life, okay? Decays to hafnium-176. Remember, zircons love hafnium. So let's start the solar system 4.56 billion years ago, and we know what the initial ratio is from chondrites. And we can measure lots of chondrites, lots of these primitive meteorites, and we know their average lutetium to hafnium ratio. So if you took the whole Earth, okay, you could, in fact, put it in that giant mortar and pestle and sampled it at 3 billion years, it would plot here. 2 billion years in the present day, it plots here. But when the mantle melts, it fractionates lutetium and hafnium. The mantle likes lutetium, so it starts to evolve above the average chondrite line. And the crust, that's this stuff here, starts to, in fact, lag behind, producing unradiogenic hafnium-176. Okay, so there's the mantle and the crust. Now, what happens if at 3.5 billion years we make a zircon? Well, the zircon's got a tiny bit of lutetium, but it's got bags of hafnium, 1 or 2% hafnium. So essentially, there's going to be no more radiogenic ingrowth. And this zircon, when we measure it today, we're going to, in fact, be able to extrapolate back in time. So that explains this diagram. Oh, sorry, let me do one more step. Just to simplify things, let's take this global bulk evolution, the bulk silicate evolution, okay, of the Earth, and let's, in fact, make that epsilon hafnium equals 0. So whenever during any period of time at 3 billion years, epsilon hafnium 0 is there, the zircon is going to plot in the negative field. So we're going to take that line and we're going to flatten it, okay? So that's the global evolution there from 4.5 billion years to present day. There's the crust evolving here, the mantle evolving here. What do the Jack Hills, what do these ancient zircons look like? Well, in fact, this is a forbidden zone. This is how the initial hafnium isotope composition of the solar system propagates through time, okay? And yet there's some zircons, 4.38 billion year zircon here, that are almost touching that forbidden zone. And what that means is that zircon there has to have been taken out of the bulk global silicate Earth system, the bulk average system, and separated into a reservoir that has never been remixed again since it formed, okay? So if we, in fact, then back extrapolate these samples here to the origin, in fact, what we get is that whatever formed the moon, if it was a Mars-sized collision, that has to be over by 4.51 billion years. Whatever formed the core has to be long over by 4.5 billion. If there was magma oceans on the planet, 1 or maybe a dozen, that's all over by 4.5 billion years, okay? Now, it's true, that zircon's only 4.38 billion years old, but it's holding information that says the global silicate system has not been remixed since 4.51. And here's some recent data from zircons from the moon, in fact, arrives at the same conclusion, that in fact, lunar formation has to have been over by 4.51. So now we've got a bound on when first solids formed at 4,567 million years. We've got pretty good evidence that the core formed 30 million years later. And now the global silicate system, so we have to in fact have reached essentially 100% of Earth's present mass and finished primary differentiation by 4.51 billion years. So the age of the Earth is a problematic concept in an active, continuously differentiating, chemically differentiating planet. There is no object on this planet that is 4.5, 4.56 billion years old, like that primitive chondrite that fell in potentially yesterday. There's just been too much activity, too much tectonic mixing for that to happen. But we can use modern isotopic methods to make some constraints. Okay, now just wrapping this up, given everything that we know, let's take a step back and ask ourselves, when did life begin? Because again, the consensus for 60 years is that life couldn't have formed prior to about 3.8 billion years ago, because that's when the well-known late heavy bombardment occurred. In fact, there's several modern critiques that suggest that this canonical event didn't happen at about this time here. So how would we in fact get evidence of life at a time when we have no rock record? Okay, well, for the past 540 million years, the time we call the Phanerozoic, here's how we do it. We want to know how old this trilobite is here. So there's a granite, and look, it's got zircons in it, and we date those zircons, and they're 450 million years old. Well, this sediment that the trilobite's in, that's sitting, what we call unconformably, on this eroded granite. So we know that trilobite's younger than 450 million years, but that sediment is cross-cut by this basalt, by this magma here, that we've taken a zircon and we've dated it to be 425. So in fact, that's how we know how old that trilobite is. Now, beyond 540 million years, we lose macroscopic fossils like that trilobite, but we still have something going for us. We've got microfossils. Actually, we've got microfossils and rocks going all the way back to 3.5 billion years. In addition, we have this, the ratio of carbon-13 to carbon-12. Okay, in inorganic carbon, in the carbon that's forming coral reefs or limestones. For 3.5 billion years, the record that we've got, it's had a ratio of carbon isotopes in this notation, this del C13 notation, that approximates 0, okay? So inorganic carbon for 3.5 billion years has a del C13 ratio of 0. In these sediments that go back 3.5 billion years, many of them have a kind of a goo, an organic residue. It's called kerogen. It's what's left of whatever life forms were in the rock, whether it was plants relatively recently or microbiota through this long period here. You can see we have prokaryotic fossils that go back as old as about 3.4 billion years. So when we analyze the carbon isotopes, by gosh, they've been minus 25 this entire period. Well, if we want to know about life prior to 3.5 billion years, we've no longer got these guys. The rocks, in fact, have been cooked up so much that there'd be no opportunity to see any kind of morphological fossil. There'd be nothing that looks like a trilobite. All you've got left is graphite after, in fact, the thing has lost its hydrogen, nitrogen, and so on. So we can look at rocks in this age here and try and identify graphite that may in fact be biogenic in origin, and one of the signals would be a value of del C13 of about minus 25. What do we see? Well, we have a rock from Greenland here at 3.8 billion years. It's characterized by carbon in this interval. How do we go back into this period, the Hadean? Well, in fact, here's a sliver of a zircon that's 4.1 billion years old. Okay, it's 100 million years old, older than any known rock. And with the assistance of Wendy Mao and your fabulous facilities here, we in fact were able to identify, at least with Raman imaging, graphite inclusions in this sliver here and here. I can show you a movie that Wendy made of the oops. Here we go. There are those two graphite inclusions there. They're not on cracks. This is primary. This is graphite that was incorporated into the zircon during the Hadean, 4.1 billion years ago. And well, I've already given away the punchline. The carbon isotopes are a dead ringer for, in fact, what we would see today as classic Kelvin cycle photosynthesis. Does it have to be biological in origin? There are abiotic ways to make it. They're kind of like a Rube Goldberg contraption in order to put light carbon like that into an igneous zircon. But even if we haven't proven that there was life 4.1 billion years ago, we in fact have discovered a pathway to understand or to be able to trace carbon isotopes through this period of Earth history that recently we thought was characterized by a continuously molten surface. Instead, we see zircons that are forming what looks like subduction zones, producing granites with a chemistry that indicates multiple cycles of sediment cycling in the presence of liquid water. Okay, so we'll wrap this up here. I hope there's some questions. Basically, you can't date Earth unless you were to take this whole body and put it into that, that giant mortar and pestle and crush it up. Then we, in fact, could calculate an age. But for a body that's been active tectonically for 4.5 billion years, what we can do is to use little fragments that have been left over, material as old as 4.38 billion years, to infer the presence of a completely differentiated silicate system that has in fact not subsequently been remixed by 4.51 billion years, the presence of the likelihood of core formation by 4.54 billion years following first solids forming at 4,567. And lastly, if there's a recurrent theme through this talk, it's that, we've been getting ahead of ourselves for 3,000 years. We're actually getting back to an estimate close to the one made 3,000 years ago. But we're probably, much of what I've told you today will turn out to be wrong. But at least it's based on observational evidence and not a scientific community collectively creating a convention that they propagate to their next generation. Thanks.
Okay, we have time for questions. While you're thinking, I want to ask one right away. Carbon-13 has a very short half-life. How can you...
14. Yeah, 14. Carbon-13 is stable. So we've got as much 13 as we had 4.5 billion years ago.
Sorry.
Yeah.
So you answered my dumb question. So if I can ask a dumb question, anybody else can ask one. Good, dumb question.
Try to first make sure I understand narrative sequences, and I tend to think time forward from the sun forming. So the evidence that for magma oceans was saying that the last time at which there could have been an Earth covered with magma is sort of 60 million years
Right,
after
451. Right, and here's something that's equally fascinating. There is no evidence, there is not a single bit of observational evidence that says that we ever had a magma ocean. That's something that we accept by convention. There's too many energy sources to conceive that it wasn't there. But this is important. There is actually no evidence that requires that we ever had one. Even if we might have had 10.
Is there, and that last one, assuming I should believe the moon forming collision, like you were telling me, maybe I shouldn't, was triggered by the moon forming collision event, right?
No, it's the 4.51 is simply the last time that the source of the material that would eventually form that zircon was participated in a globally mixed system. It could have been because of a magma ocean. Certainly if we did get hit by a Mars-sized impactor and shoot off the moon, that would have been a very traumatic day in Earth history. And you can imagine there would, a lot of mixing would have occurred. But if that happened, it had to happen before 4.51, whereas until relatively recently, there have been advocates of a young moon forming as late as 4.35. That just didn't happen.
Because where I'm interested in wearing my observational hat is how old could a planetary system be and still have a decent chance of its Earth analogs having a mostly molten surface? Because I could imagine techniques that would allow us to detect extraterrestrial magma planets?
You know,
That's all I'm looking for.
contemporary models of magma ocean evolution, depending on whether you have an atmosphere or you don't, they don't last hundreds of millions of years. They last tens of thousands or 100,000 years maximum. The convection's just way too vigorous. It's a great way to cool a very hot, energetic early planet. Yeah, put an atmosphere on and things slow down, but you know, it would be very difficult to conceive how you would keep a magma ocean going for hundreds of millions of years.
So the moon seems to be the same age as the Earth?
Well, the moon is easier for us to date because it's been dead for a long time. So there's been less mixing and remixing. So we, in fact, can go to the lunar surface and find zircons that are older than 4.4 billion years. So we have those in hand. When we take those zircons and ask the same question with the lutetium-hafnium isotope system, it extends back to 4.51, just like Earth. So this could be a coincidence, but the appearance is that, you know, something profound happened 4.51 billion, or stopped happening at 4.51 billion.
Thanks for your fascinating talk. I'm curious where this is all going with computer modeling. Say you were able to create a realistic version of Google Street View
Is that me?
a Google Street View with time slider and add all the periodic elements from the periodic table and create algorithms.
You can stop the question. I can answer it right now. Never. No, you know, mantle convection is you know, a chaotic, nonlinear process that it's simply not possible to do an ab initio calculation, even if you could put in all the parameters, compressibility and you know, nonlinear rheology. And in fact, recently a couple of papers over the last couple of years have shown that actually mantle simulations, sophisticated mantle simulations, are path dependent. And as you take an Earth structure, you arrive at that structure from one path, bring it so it's exactly, they arrive at exactly identical thermal and inertial structure. They evolve subsequently on different paths. So it simply will never be possible to use calculation to reconstruct. We're going to have to do this the hard way. We're going to actually have to go out and find fragments from which we can interrogate, make measurements, devise systems we haven't even thought of yet to winnow out the details. And one thing I didn't mention, I said constancy of physical laws, the old zircons and isotope and all. There's the surface of the moon. Half of it is probably Hadean. So let's get back there and get to work.
So as a follow-up, what happens if we could all, geologists in this room, add our data, add our video, add our images at the molecular level to this realistic version or the time slider to fill out the more chaotic processes that you're characterizing? Is that on the horizon?
You know, I think that in fact that would be a step back to where we create a convention, we create a tribal myth, and we propagate from, you know, the basis of what limited data we have. I think that's the direction. In fact, is to there was a calculation, interesting calculation made 15 years ago by a guy named Harrison, who determined that, you know, for some assumptions about you know, how violent the early solar system was, that the average rock, the average kilogram of rock on the lunar highlands contains more terrestrial Hadean zircons than in the Jack Hills quartzite. So our mine for Hadean zircons probably has fewer Earth-formed zircons than an average piece of lunar crust. So that's got a fantastic. We might even find bits of, you know, of terrestrial marine sediment from 4.5 billion years ago on the lunar surface. So let's take advantage. We've got this stable object nearby that's collecting our debris, lots of it early on. That's the place to look. Or at least let's get together with the Chinese that are going back.
I just have a question because the Jack Hills is just only one location that you're doing research on. And the results that we can estimate for potential are
Absolutely. There are 13 other places on the planet that have zircons that are older than the oldest known rock of 4 billion years. 5 in China, there's a couple more in Australia, there's one in northern Canada, there's one in West Greenland, there's one now just discovered in South Africa. And for years, I've been trying to get a project funded, which in fact is to do the same thing for some of these other sites that have, for at least we know the presence of one Hadean zircon. Let's go on to an analytical jihad and find 1,000 more from this site. And I've now been rejected 5 times on 2 different continents by 3 different agencies, and the message is always the same, that this is a fishing trip. Yes, it is a fishing trip. It's called discovery, and for some reason, we don't do it anymore. We have to have a hypothesis-based proposal, and my only hypothesis is I hypothesize that there might be more of these Hadean zircons, and we can't get it up. So I would love to in fact find a location that contradicts the story that we're getting from, because the planet can't have been in a single mode. If you were to sample the planet today, not every rock would look like it came from a subduction zone. So we have tremendous opportunity, and what I've said in the course of maybe this is why the proposals get bumped, is if you gave me 7% of what a typical NASA planetary mission costs, I could give you 1,000 zircons with carbonaceous inclusions from the Hadean from multiple sites. And for some reason, that's not appealing. How accurate is? Oh, no, that's it's reasonably well measured. It's hard to do these betas because, there's obviously a spectrum, and, you don't know how this has gone out in the neutrino. But so what's done is we've got the uranium-238 and 235 decay constants nailed down to, a 1/10% precision. So what's been done is folks find geological occurrences where zircons formed. We date those by the uranium-lead method, date the rock by lutetium hafnium, and then infer that assume that the systems have remained closed, and that's how we're getting these decay constants. It's a tough measurement for sure. But these data that we get from this natural approach are consistent within the uncertainties of the physical measurements. I think we've.
Okay, the timing is perfect. I have one more question, but I'm going to say it. Let's thank our speaker.
Thank you. Oh, that's great.